Imagine two particles, born from a single event, flung to opposite ends of the universe. They exist billions of light years apart, with no conceivable way to communicate. Yet, despite this immense distance, their fates remain intertwined. Measure the properties of one and instantaneously the properties of its distant twin are determined. This is quantum entanglement, a phenomenon so bizarre, so counterintuitive, that even Einstein famously dubbed it spooky action at a distance. Entanglement speaks to a connection deeper than anything our classical intuition can grasp. It defies our everyday experience of cause and effect, suggesting a universe far stranger and more interconnected than we ever imagined. This perplexing connection, this ghostly dance across the cosmos, lies at the heart of quantum mechanics, challenging our very understanding of reality. The implications of entanglement are profound, extending far beyond the realm of theoretical physics. It hints at the potential for unbreakable encryption, instantaneous communication across vast distances, and a new generation of computers capable of solving problems that would take classical computers billions of years. But before we explore these tantalizing possibilities, we must first delve into the heart of this enigmatic phenomenon. To grasp the essence of entanglement, let's imagine a simplified analogy: two coins, meticulously prepared and flipped simultaneously. These are no ordinary coins. They exist in a quantum world where possibilities reign supreme until the moment of measurement. Before we look, each coin exists in a state of superposition, a blend of both heads and tails. Now imagine these coins are entangled. This means their fates are intertwined. If we observe one coin and find it heads up, we instantly know the other coin, no matter how distant, must be tails up. This connection is not about a predetermined outcome, it's about a shared fate established at the moment of their quantum birth. This analogy, while imperfect, captures the essence of entanglement. In the quantum realm, particles like our coins exist in a haze of probability until measured. Entanglement ensures that the act of measuring one particle instantaneously determines the state of its entangled partner, regardless of the distance separating them. This behavior challenges our classical intuition, where objects possess definite properties independent of observation. In the quantum world, entanglement reigns supreme, underscoring the deep interconnectedness woven into the fabric of reality. The very notion of entanglement deeply troubled some of the most brilliant minds in physics, including Albert Einstein. He, along with colleagues Boris Podolsky and Nathan Rosen, proposed a thought experiment in 1935 that aimed to expose the supposed absurdity of entanglement. This thought experiment, known as the EPR paradox, challenged a fundamental tenet of quantum mechanics locality. The EPR paradox argued that if quantum mechanics were a complete description of reality, then entanglement implied faster-than-light communication between entangled particles, violating Einstein's own theory of special relativity. Einstein believed this spooky action at a distance indicated a flaw in quantum mechanics, suggesting the existence of hidden variables, yet unknown factors that predetermined the outcomes of measurements. Einstein championed local realism, the idea that objects possess definite properties independent of observation and that no influence can travel faster than light. Entanglement, with its apparent disregard for distance and instantaneous correlations, seemed to contradict these cherished principles. This clash of titans between the elegance of quantum mechanics and the intuitive appeal of local realism set the stage for one of the most profound scientific debates of the 20th century. For decades, the debate over entanglement remained a philosophical quagmire. Then, in 1964, physicist John Bell devised a brilliant solution, a testable inequality that could experimentally differentiate between the predictions of quantum mechanics and those of any theory based on local realism. Bell's theorem provided a way to cut through the philosophical fog and settle the debate through the concrete language of experimental data. Bell's inequality, when applied to entangled particles, predicted a specific limit on the correlations between their measured properties if local realism held true. Quantum mechanics, on the other hand, predicted correlations that could surpass this limit. The stage was set for a showdown between two fundamentally different views of reality. Beginning in the 1980s, a series of increasingly sophisticated experiments, spearheaded by physicists like Alain Aspect, put Bell's inequality to the test. The results were clear. The predictions of quantum mechanics were consistently confirmed, while local realism was decisively refuted. The spooky action at a distance that Einstein found so unsettling was not a flaw in quantum mechanics, but a fundamental feature of the universe we inhabit. The experimental validation of entanglement ushered in a new era of exploration, pushing this once bizarre phenomenon to the forefront of technological innovation. Entanglement, once relegated to the realm of theoretical curiosities, is now being harnessed to revolutionize fields like computing, communication, and cryptography. Quantum computers, for instance, leverage the entanglement of qubits, the quantum equivalent of bits, to perform computations impossible for even the most powerful classical computers. This has the potential to revolutionize drug discovery, materials science, and artificial intelligence, unlocking solutions to problems that have long remained intractable. Entanglement also holds the key to unbreakable encryption through quantum key distribution. By encoding information in the entangled states of particles, any attempt at eavesdropping would inevitably disturb the entanglement, alerting the intended recipients to the breach. This promises a future where sensitive data, from financial transactions to state secrets, can be transmitted with unparalleled security. Beyond its technological promise, entanglement forces us to confront profound philosophical questions about the nature of reality, locality, and the relationship between observer and observed. If two particles can remain instantaneously connected across vast distances, does this imply a fundamental interconnectedness to the universe? Does it challenge our understanding of space and time as we know them? Entanglement compels us to rethink our classical intuitions about causality. If the act of measuring one entangled particle instantaneously determines the state of its distant twin, can we truly claim that one event caused the other in the traditional sense? Or does entanglement point to a deeper, more holistic view of the universe, where seemingly separate entities are fundamentally interconnected? These questions lie at the forefront of modern physics and philosophy, pushing us to expand our conceptual frameworks and embrace the strangeness of the quantum world. Entanglement, in its defiance of our everyday experience, offers a tantalizing glimpse into the profound mysteries that still shroud the universe. Quantum entanglement, once a source of deep skepticism and heated debate, has emerged as one of the most profound and well-established phenomena in physics. From its humble beginnings as a theoretical curiosity to its burgeoning role in cutting-edge technologies, entanglement has captured the imagination of scientists and the public alike. While our understanding of entanglement continues to evolve, one thing remains clear. This spooky action at a distance is not a quirk of the quantum world but a fundamental feature of the universe we inhabit. It speaks to a deep interconnectedness, a cosmic dance that links particles across vast distances, challenging our classical intuitions and revealing a reality far stranger and more wondrous than we ever imagined. As we delve deeper into the enigma of entanglement, we embark on a journey of discovery, pushing the boundaries of knowledge and reshaping our understanding of the universe and our place within it. The story of entanglement is far from over. It is a story that is still being written, one experiment, one discovery, one mind-bending revelation at a time.